Is that a question in the original one?
Yeah. So I have 1201, so we go ahead and get started. I'll take questions at the beginning. Does anyone have any questions over Wiley? On Wiley? Okay, so we had a question before class on 5.3, number 26, and it turns out A and B are A is pretty straightforward. B, if you actually go through the U substitution step, it turns out you're going to have 1 over the derivative of U out front. Then sine inverse, and that doesn't really show up here. Because it's not 1 over A, it's 1 over the derivative of U. So if you plug that one in and you don't know why it's not working, it's because you need this, arc sine of U over A, but when you pick U, you need a du to cancel. So 4x would be your U, so your du is 4 dx. So you need a 1/4 out front to manipulate that, right? Because if I write a 4 in here, then I have a 1/4, and then I have the 1/4 to pull through. And then C, again, is pretty straightforward. This answer they accepted to be correct here. So 1 over A, and A is the square root of 3. Arc secant, or secant inverse of U, which would be square root of 5x, divided by A. Question?
So I didn't look at the formulas up top. I just started doing U substitution, and I got different stuff. I didn't end up submitting them to see if they were correct because for the third one I was having trouble, and then I looked at the formula.
Mm-hmm.
But could you do it?
You could do it out the formula, but it would be
It was a different
counterproductive.
answer.
It should be the same answer, so that's not. It's a little concerning. That was a different answer. So yeah, the U substitution here, you have to kind of go about that and think about that to get the constant out front. And then once you do that, the form is exactly what you want. So students like, do I have to memorize these formulas? And you wouldn't necessarily have to memorize. I would say memorize the formulas with A is 1 for tangent inverse and sine inverse. Pretty straightforward if A is going to be 1, right? When A is something other than 1, it's not as straightforward with the U substitution, so I memorized them with A being 1. Question?
Yeah, on the bottom formula,
Mm-hmm.
for A,
Yes.
can you go back up to the formulas? I couldn't figure out if A would be negative or positive.
A is positive.
But if you square it, wouldn't negative A be the same?
Yeah, but then you would lose the plus there. And it would look something like cosecant? No, cosecant inverse is something like that. So this comes from trig identities. I'm going to tell you. In Calc 2, you would do trig substitutions, and it turns out you're going to use the formula as sine squared plus cosine squared is 1. So if you have 1 minus something squared, you're going to replace that with cosine. 1 minus cosine squared could then replace with sine squared. And the square root of sine squared is sine. So these types of identities kind of come from this trig substitution that you would learn in Calc 2 if you take Calc 2. In Chapter 7, Techniques of Integration, doing trig substitution. So
it's the same book, right?
it is the same book. It's the same book, the same Wiley, the same everything. So hopefully that clarifies some issues on B, because you need that 1/4 out front, and then also on C. Here, if I get rid of the minus 3, if I take that to be A and I square it, I get rid of the negative, which takes me away from that form of secant inverse. So A is positive. right? Any other questions on Wiley? So there was a question on the written homework. What question do you have?
9A,
On what section?
5.3.
5.3. So we're looking at 5.3, number 9A. So we want to see, this is a U substitution, and it's telling us what to pick to be U. So this is 3.5, number 9, part A. And we're integrating 1 over x, ln of x, with respect to x, and they told us to have U be ln of x. Right? So now, really in U substitution, that is the hardest thing to find, the U. Once you've found the U, everything follows through from that. So du, what is the derivative of 1 over x? 1 over x dx. Which we have 1 over x dx. We could replace that with, so we really have the integral of 1 over u du. Do you guys see that? Another way to see that is I could solve for dx. Dx is x times du. So then I have the integral of 1 over x times u, x times du, and the x's cancel. And I get 1 over u du. What is the integral of 1 over u? It's ln of the absolute value of u plus c. But if I plug that in, I have ln of ln, I have ln of absolute value of ln of x plus c. That would be my answer.
So like, what I'm confused about, like, how do they get?
Oh, sorry. And you can see that is the correct answer there.
The ln of absolute value of ln x.
Yes.
When they are like taking the derivative of ln x divided by ln of b, ln of x, it turns out to be ln of x, and I don't even know how they got that.
The derivative of ln
X divided by ln x.
divided by ln x?
Yeah, like I have like bx, no, b to the power of x divided by ln of x.
Yeah.
And they got the answer to be b to the power of x.
Yes.
So I don't know how they got
On the part B?
that. No, like this one is on like 5.2 where they wrote the derivative.
Yeah.
But I don't really, because the answer is like the same thing with this.
Yeah.
So I don't really know how they get each other. I don't know.
So you're asking b dx over ln of b, and you're asked to find the derivative of that.
Yeah.
Well, the derivative of b to the x is ln of b to the x, right? ln of b times b to the x, and then ln of b is just a number. The ln of b is cancel, and you get
Wait, the derivative of b to the x.
the derivative of just b to the x. The derivative with respect to x of b to the x is ln of b times e to the x. Oh, b to the x, sorry. Oops. In this special case when b is e, the derivative with respect to x of e to the x is really ln of e times e to the x, but ln of e is 1. But if I wanted to know what the derivative with respect to x of 2 to the x, that's ln of 2 times 2 to the, I'm so stuck on e, ln of 2 times 2 to the x.
So they're using this in terms of like e to the x.
The derivative of e to the x is e to the x. The derivative of anything else to the x is ln of that anything times that anything to the x. So the derivative of 52 to the x is ln of 52 times 52 to the x. E to the x is a special case when the derivative is e to the x.
So because what I did was like I said x ln of b, because I don't know when you do that. When we use the ln to bring out the power.
This is a totally different setup. This is saying they're telling you your u is ln of x, so your du is 1 over x. So that gets your integral in this form. Do you understand that?
Mm-hmm.
So you know how to integrate 1 over u.
Yeah.
The integral of 1 over u is ln of u. So then you're done, except you need to back substitute what u is in terms of x. So you have ln of u, and u is ln of x. So you have ln of x. If I differentiate this, I get back with what I start with, which would be 1 over ln of x times 1 over x, which is exactly what I started with. If I differentiate this with respect to x, I get 1 over x times ln of x, which is where I started. Any other questions on the written homework?
Is that just a rule we're supposed to memorize, that it's going to be the absolute value? Because, I mean, I understand absolute value when it comes to, like, squared and square root.
So the rules here, we have x to the r dx is x to the r plus 1 over r plus 1, right? This is only when r doesn't equal minus 1. And then the integral, when you have x to the minus 1 dx, that is ln of the absolute value of x plus c. The reason why we have absolute value here is because we cannot take ln of a negative number. You can't take ln of 5. You can't take ln of minus 5. ln of minus 5 doesn't exist. You put it in your calculator, it will say domain error. Because natural log doesn't exist for negative numbers. Because e to the x can never be negative. Natural log and e to the x are inverses of each other. So if I plug any number into e to the x, it's going to be positive. It will never be 0 and it will never be negative. So that means I can only take natural log of what I can plug in, what I output of e to the x, which is only positive numbers. Question?
So that last one where you wrote the derivative of e to the x, would it be x e to the x, or is it just natural log of e?
It's natural log of e times e to the x. Natural log of e is 1.
Okay.
ln of e is 1, right? It's kind of like log base 5 of 5 is 1.
But is there actually also a chain rule there where you're doing the derivative of the power of x? And
If-
that's one's also.
Yes, here, yes. If I would have what is the derivative of e to the 2x, it would be e to the 2x times 2. Yeah, so here that would be 1 as well. But if I wanted to do the derivative with respect to x of 2x squared, this would be ln of 2 times 2x squared times 2x. Really, this doesn't mean a lot, but it would potentially mean e to the x is very useful in solving exponential type functions. Exponential rate of decay, these mean things in biology and physics and stuff. Here, you could have something that is base 2, but you can always convert something base 2 into base e and deal with it that way.
So like if you're having something like x to a number, it would be like in a different case.
Yes. X to a number is just basic power rule, right? The derivative of x to the 5th is 5x to the 4th, right? The integral of x to the 5th would be x to the 6th over 6. But this is different because you're taking a variable to a power that's you're taking a number to a variable power versus a variable to a specific number power. Any other questions on the written homework or Wiley homework? Yes. On the same section?
Yeah.
On the written? 12A. So we're going to expect this to be a sine inverse one, and this to be, this is just going to be u, a less apparent substitution. So let's look at 12A. Number 12A, we have the integral of dx divided by the x, the square root of 9x squared minus 1, and u is to be 3x. So it's nice they tell us kind of what to pick here. So if u is 3x, du would be 3 dx, right? So if I want to manipulate my integral, I can put a 3 in here and then multiply by a third. So if I do that, I have 1/3 the integral of du over, I have x, the square root of u squared minus 1. Now I have a problem with this x. Is there another way I could write it?
U divided by 3.
U divided by 3. See if that gives me what I want. Okay, so 1/3 the integral of, if I had u over 3 here,
Just put the 3 on the top.
yes, I could. So then I have 3 over u, the square root of u squared minus 1 du, right? The 3's would cancel at that point. Do you know this form?
So it's second.
Secant inverse of u, right? Secant inverse, is it absolute value? I believe it's absolute value of u. From that, 5, 3. And 5, 2. These are listed. No, wait, no, sorry. Yeah, it's absolute value. So we lost the 1/3. And I know I need a 1/3. See where I lost that at. No, wait. Do I need a 1/3 with secant? I do not need a 1/3 with secant. I'm sorry. That is correct. This would be correct here. So if we look at our form, and since this is here, and I want to compare it to secant inverse here. What is A? Forget the red 3's. What is A? 1. What is U?
3x.
So if I plug that in, putting this back in terms of x, I have secant inverse of the absolute value of 3x plus c. So I have no 1 over a because a here is 1. Does that make sense? So you could know the form of the integral of dx over, I'll just leave it as x, the x squared minus a squared to be secant inverse of the absolute value of x over a, 1 over a, plus c. So here a is 1, and x being the u, x would be 3x, would be playing that role. But do you see how doing u substitution, you see that the 1/3 cancels the 3 and getting it? Question?
Can you do, I think it's like number 20, something on the written homework on the first section.
On the first section.
Is that 4?
So we had the exam up to 4, 8.
Yeah, I think that's what it was like about temperature and how it's this
Yeah.
temperature at 11.
Oops. 3, so 4, 8. Number 20, Rolle's theorem. So on number 20 it says, and this is just to kind of show what's going on here. So at 11 a.m. a certain morning, the outside temperature was 76 degrees Fahrenheit. And by 12 p.m., 12 hours later, sorry, by 11 p.m., 12 hours later, in the evening, it dropped 52 degrees. So if you find the average rate of change, at some point in time, the instantaneous rate of change has to also be 2 degrees. So this is 7.8, number 20. So I have f of, let's say, 11 p.m. minus f of 11 a.m. over the 12-hour difference. So let me kind of keep this up here. So, oh, sorry, I mean Calc 2. 4.8, thank you for clarifying that. So we're looking here, this problem here. So we'll change this to 4.8. So at 11 p.m., the temperature was 52 degrees. So 52 minus 76 over 12. So I have 52 minus 76 divided by 12 gives me a minus 2 degrees Fahrenheit an hour. Minus 2 degrees Fahrenheit per hour. That's an average rate of change. So show at some instant during the period the temperature was decreasing at a rate of 2 Fahrenheit an hour. So that's the way to show that, right? The mean value theorem states that the average value at some point in this, Rolle's theorem in, not the mean value theorem, Rolle's theorem, help me with the other name, oh, mean value theorem. So mean value theorem in Rolle's theorem states that the slope of the secant line, that has to be some point in there where it has this tangent line is the same slope. So some point in this interval, I'm decreasing at 2 degrees an hour. Suppose that you know temperature reaches a high of 88 sometime between this. So show that the temperature decreasing at a rate greater than this. So the same thing as saying I started at 52, I started at 78, but if I subtract 88, was it 88? Over some time less than 12, right? This is something less than 12 hours. The difference between the ending temperature and the high is going to be, what, 52 minus 88. So if I take 52 minus 88, I have minus 36. If I let it be the full 12 hours, this is minus 3 degrees Fahrenheit. If I divide that by anything less than 12, it's greater than 3 degrees, right? 12 hours is kind of the maximum it can be. So maybe at 11:01 or 11 o'clock it was 76 and 11:01 it was 88, right? That would be the maximum amount of time I could have to decrease from 88 to 52. So the slope of that secant line is still greater than 3, right? So the temperature was decreasing at a rate greater than 3 degrees Fahrenheit. Because if I let it be 12 hours, that would be a rate of 3 degrees. So this is only going to be smaller than that because it has to be some point in time between these two. So that's going to be greater than 3 degrees. Make sense? I know sometimes with speculations and more abstract problems, we kind of lose track of what we're actually doing. So it's good to kind of come back on that. But yeah, this is the mean value theorem, and Rolle's theorem is specifically stating the average value over your interval, then at some point in that interval you have to be going that specific average value.
So is this kind of the same concept as case number 21? R1?
Yes. So number 21, yeah, suppose that two runners are running a 100-meter dash finish line and they tie. So show that they have the same velocity at least once during the race. Well, they have the same average velocity. If they start at the same time and stop at the same time, their average velocity is the same. So, distance covered over the time it took is going to be the same. So their average velocity, they have to be going the same velocity at a point in time. The times don't have to be the same. I could hit my average velocity at 2 seconds in the race, and someone else could hit it at 5 seconds during the race. But at some point in time, we had the same velocity. So yeah, more of it's kind of writing up and filling it out than any calculations here. Does that make sense? And if you kind of draw a picture, and it makes sense as well. So if I drew two different pictures for racer 1 and racer 2. No, racer 1, the position versus velocity curve, or if I do velocity, let's say they started out, going really fast and then they slowed down and they finished the race. And runner 2 could start going, really slow and then they finish the race. So your average velocity, that would be, this is velocity over time.
It's whenever they cross each other, right? If you put it on the same graph. it's
No,
maybe-
because I'm looking at their slopes. Like, let's say the slope's like this. Some point in time, the slope's also like that. If they have the same slope, at some point in time, let's see, if I move it, this slope might be like this. So this might be at time 1, and this might be at time 2. This is not a very good picture. Yeah, so pretty much what I said straightforward, that if they have the same average velocity, by mean value theorem, they have the same instantaneous velocity at some point during the race. It doesn't have to be the same point, though. Some C star value.
But it'll be at the same time.
No. See, it says the same velocity at least once during the race, but not. Suppose the two runners in a 100-meter dash finish in a tie. Show that they had the same velocity at least once during the race,
Okay.
but not at the same instant in time during the race. Okay, just because that they start and stop at the same time doesn't mean that they ran the same speed every time through it, yeah. But they had to have the same at some instant, separate instances. Okay. Any other questions on the written homework or on Wiley homework?
Also, like it will be
On the same, what section?
no the 5.3.
12B?
5.3.
No, this is 4.8. So this will be the last one I have time for. 5.3. 12B. So along the same line, did you do the u substitution?
Yeah.
What's the derivative of x to the 1, or the square root of x? 1/2 x to the minus 1/2.
Mm-hmm.
So plugging in then, that's going to cancel. See if I can write this one up. You probably won't finish it completely. The integral of dx over square root of x, 1 plus x. And if I let u is square root of x, then du is 1/2 x to the minus 1/2 dx. So this would probably be better to...
What about 2
what?
What about 2 square root of x?
What about square root of x?
Like if you put it in the form of 1 over 2 square root of
The
it,
D.
like the x.
Oh,
and
I could write this as 1 over 2 square root of x. True. So if I solve for dx, I have 2 square root of x du. So I have that. If I square both sides here, I have u squared equals x. If I add 1, and I add 1, so I have x plus 1 equals u squared plus 1. So I have the integral of dx, which is 2 square root of x du, over square root of x u squared plus 1. The square root of x cancel. And then I have 2 tangent inverse of u plus c, which would be 2 tangent inverse of the square root of x plus c. Right? So this is the less apparent one. I can't just substitute this in for the square root of x to be u, because then I would have no way to cancel this 2 square root of x. So I need to leave that as 2 square root of x du. I need to leave this as dx to cancel it. I don't want to change it to u. But doing that, it gives me a way to write this to get tangent inverse, to get the answer there. Make sense? This one's less apparent. It's not as straightforward. It does take some looking at seeing what this is going to be. Giving the u substitution, it tells me that I'm going to use square root of x, and then rewriting dx in terms of u tells me I cannot replace that square root of x with u because I don't have a square root of x to cancel with my du to get it only in terms of u. So I have to leave this square root of x as square root of x. So I cancel with the square root of x on top. Then it's tangent inverse in terms of u. So then the square root of x comes back in it here. And this would be your answer there. Yes?
When's the written homework due?
The written homework will be due the Thursday before the exam. And the exam, I think, is Wednesday? The last Wednesday? No, it's on a Tuesday. So it will be due 4:30. So written homework due 4/30/13. All right, so let's move along to 5-6. And 5-6 is the fundamental theorem of calculus. And I've kind of hinted to where this is going to come into play. And now we're going to formally write it up. So 5.6, the fundamental theorem of calculus. A lot of times this is abbreviated as FTC. Fundamental theorem of calculus is a very powerful theorem in calculus. In integral calculus, more per se, is because it allows us to calculate the area under the curve using calculus instead of geometry and algebra, which, woohoo, we can apply that. So some things we have to keep in mind is the function we're integrating has to be continuous. On the closed interval, what we're integrating it along to that. And more so, capital F of x, the antiderivative, is any antiderivative. But this antiderivative works on the whole interval. So if this happens, we have the integral from a to b of this f of x dx is noted as the antiderivative at b minus the antiderivative at a. So some notation here. And I've kind of talked about this a little bit before in my examples, is that you can plug in the antiderivative and we can drop the plus c because we have any antiderivative. So we don't have to worry about writing every antiderivative. So any antiderivative, let's just make c be 0. It doesn't matter, since we're subtracting here, the c minus c would cancel anyways. So we take c to be 0. We plug in our upper bound minus our lower bound. Last time when we talked about the geometry, we integrated x from 1 to 2. Right? But now what this means, to find the area underneath this curve, we don't have to draw it. We can use calculus. And the calculus says that I find the antiderivative, and I plug in my upper bound minus my lower bound. So 2 squared over 2 minus 1/2, which would equal 3 over 2. And that's the power of the calculus, right?
What's that 3 over 2?
It's the area, right? So it might have some units squared or square units. However, in calculus, we just focus on the technique and not what it means. In 5-8, 7 or 5-8. 5-6 is fundamental theorem of calculus. 5-7, 5-8. In 5-7, we will talk about rectilinear motion revisited. Position, velocity, acceleration, right? If I differentiate position, I get velocity. What if I integrate velocity? I get position. So we're going to talk about this position, velocity, and acceleration revisited in 5.7 and 5.8. It's kind of the same thing, but they don't position, velocity, acceleration. They won't name it that. They'll say the. If I take a function, I differentiate it, I get another function. If I integrate it, I get the original function. So it might say, what's the original function? And then we'll talk about average velocity, average rate of change, things like that, and how to calculate using integrals. So let's look at some more examples here. I want you guys to do this one. The integral from 0 to 9 of 9 minus x squared dx. We kind of looked at this one on Thursday. I think we had time to look at this one on Thursday. Using the summation notation that the book talked about. The getting there took 2 or 3 pages. So fundamental theorem of calculus will take 2 or 3 lines. This is the algebra approach.
Well, we didn't use the algebra approach on
No. So generally we teach the algebra approach, but it never comes up on the final. But this semester we decided to just cut it out, and then so we can get to 6.1 and 6.2 and 6.3, which would come up on the final. So the algebra approach, we told them none of the Calc 1 sections are covering 5.4, so do not put anything from that section on the final missing. So I'm just going to walk around and look at your notation, because notation's a big thing here. Most of you, probably the first mistake you'll make is you will not integrate 9 credits. What's the integral of a constant? 9x. Right? Yeah, but yeah, that would be 0. Okay, so here. Oh, I see my problem. It might be negative. I'm sorry. Let me go ahead and fix this. Just so we're consistent on what we get. It's 0 to 3, not 0 to 9. Sorry. This would be 0 to 3. Just so we're consistent with what I have. But I think your antiderivatives were correct. That'll be easier to calculate. It's 9 cubed is not too fun.
Just cancel out the 3 months, cancel out the 0, cancel out the 0 to 0. So it's whatever cancel out to get to 50 is.
Did I write them all? I did.
This is a quadratic. It's shifted up 9 and reflected, right? So if we look at the graph of this, I'll go ahead and write it here.
For 9, I think it's 1
No, she's changing.
I don't think what's crazy.
Yeah, this would be 0 to 3. So I really want to find this area, which would make sense because it to be positive. Versus if I want to find from 0 to 9, we would expect a very negative number, right? So if we did that. So we would expect that to be negative, but I want from 0 to 3. So my antiderivative is 9x minus x cubed over 3. I plug in my upper bound minus my lower bound. So I have 9 times 3 minus 3 cubed over 3 minus the quantity 9 times 0 minus 0 cubed over 3. So I like to break these up so I know it's this number minus this number, because if you're not careful and you drop that, you can be adding numbers where you should be subtracting numbers and subtracting numbers where you should be adding them. So here we get, see if I even have this one. I get 27 minus 27 over 3, which would be 18. Does that make sense? Yes.
Can you explain conceptually what f of b minus f of a, what that means?
Yeah.
This means you take the antiderivative at b minus the antiderivative of a. You're finding the, okay, so if this was a velocity, the average velocity would be the change in position, right? So you would take the change, the position, and then you divide it over time if you wanted the average velocity. But I might want to know the difference in velocities or the difference in positions. So if I integrate something, if I integrate a velocity function, I get position. And the difference in position, if I divide by time, that'd be average velocity, right? So this is, it's kind of where this is coming from. The proof for this is in the book, and if you really kind of want to see where this is coming from, so the fundamental theorem of calculus here. So the proof is saying, okay, let's take intervals in between a and b, right? So the values, if I divide them up into subintervals, look like from a to x1, x1 to x2, x2 to x3, all the way up to n minus 1 to b. So I have n subintervals, and I can use this delta x1 notation as the differential in each subinterval. That's the length of each subinterval. So if I go through and do this calculation, the value of the function at x1 minus the value of function at a is going to turn out to be the value of the function at x1 times the difference in x1 minus xy, which would be the value of the function times the differential, the area of that rectangle, right? If I sum them up, I get the difference fb minus fa. So here being, subintervals, if I come in here and do this, and I take the limit of the maximums, I get the integral, which is the fundamental theorem of calculus. So you can go through the proof, and there's some online. It would take, 30 minutes, sit down and watch it to get it. We don't have the time in class to go in that much detail. Well, we want to say, what does this mean? So someone asked, what does this mean? This means the area underneath this curve from 0 to 3 has an area of 18 units squared. If I want to integrate from 0 to pi of cosine of x dx, well, if I look at the graph here, I have, 0 to pi. What would we expect the area underneath the curve being? 0, right? So if I calculate this, what's the integral of cosine? Sine, the integral of cosine. Sine, right? The derivative of sine is cosine. This is the most common mistake. This is what I see all the time, is putting negative, right? So write it down. Take a minute. Say, what's the derivative with respect to x of sine? Well, that's cosine. Well, if I integrate cosine, sorry, that looks not like cosine. If I integrate cosine, I get positive sine. The derivative of sine is cosine. So if I integrate cosine, I get positive sine, which would be 0 minus 0, which is 0, which makes sense, right? What do you think the 0 to pi over 2 of cosine is? Integral from 0 to pi over 2 of cosine of x. Well, that would be pi over 2 to 0. So I have sine of pi over 2 minus sine of 0. What's sine of pi over 2? 1, right? So if I zero to pi over 2, if I was to calculate this, I would have 1 minus 0, which is 1. So So the integral from 0 to pi over 2 of cosine is 1 unit squared. Which we would not be able to do that without calculus, unless we wouldn't apply the algebra technique, right? Because I can't box this into a nice rectangle and find the area there. So there's plenty more you could go through and see examples of. In the last 5 minutes, I want to talk about the warning here. So for the fundamental theorem of calculus, f of x must be continuous on AB. Calc 2 in 7.8, you'll focus more on what happens when the function is not continuous. That's an improper integral. But if I wanted to integrate minus 1 to 1 of 1 over x squared dx, would you agree that this function's always positive? Right? If I take a number and square it, 1 over that's always positive, right? So it's not negative. So the area should be positive, right? So let's apply the fundamental theorem of calculus. So what's the integral of x to the minus 2? X to the minus 1 over minus 1, right? If I plug in my upper bound minus my lower bound, I have 1 over minus 1 minus 1 to the minus 1 over minus 1, which would be a positive one, right? So I have minus 1, which is minus 2. That gives me an error, right? How could a positive function have a negative area? It's because the fundamental theorem of calculus fails at x equals 0, which is in this interval. So I can't apply fundamental theorem of calculus to something that has a discontinuity in the interval. And then the fundamental theorem of calculus works on piecewise functions, but you have to divide them up. So let's say I have the integral from 0 to 3 of f of x dx, and let's say my function is defined as x squared if x is less than 2, and 3x minus 2 if x is greater than or equal to 2. So if I wanted to find this area, I would integrate from 0 to 2 of x squared dx plus the integral from 2 to 3 of 3x minus 2 dx. And I could find that simple enough. So the piecewise functions can be separated into intervals in which they are defined as. So the area from 0 to 3 is going to be broken up to find the area on the interval from 0 to 2 plus the area on the interval from 2 to 3. So you integrate each interval separately and then add them together. Fundamental theorem of calculus will take into account if your function is negative. So that's nice to know that. You don't have to graph it. This will work. But you wouldn't just integrate from 0 to 3 of x squared because the function is not defined at as x squared at 3. So you can break this up into subintervals.
Well, the ones where there's an error, will they bother?
You won't have this type in Calc 2. In Calc 1. This is a Calc 2 problem. But I wanted you to not just take advantage. Fundamental theorem of calculus always works. It will in Calc 1. But in Calc 2, you'll have to take a note that the function has to be continuous. Now, I can integrate this from 5 to 10, no problem, in Calc 1. Because that doesn't involve the point 0.
You always add, piecewise, you would always add them together.
Yes. Yes.
Basically, you're accumulating it.
Yes. All right, I'll see you guys tomorrow.